So I'd like to talk about some aspects of stability when I'm dealing with sort of linear state equations. In particular, sort of you can imagine what would happen if I have a general set of linear state equations. We usually talk about a couple different forms of stability, and I just want to kind of list them a little bit, and sort of what their mathematical definitions are. So certainly if I have an unstable system, that would mean if I took y of t by some norm, and again, remember norms have this sense the same way that Lyapunov functions do. There's a range of them, and if I can get it with some of them, it makes sense. The key would be as if that norm is unbounded somewhere over the time trajectory of the differential equation system. Now, in a linear time invariant system, that's typically going to be when the coefficients are constant, maybe like what we would see over here. What that's basically going to be having one of the eigenvalues is going to be greater than 0. The second case I get is marginally stable, which means that is this signal now always bounded in a norm over that range, which it means in a linear time invariant system. So for the constant a, and again the dynamics are typically going to be set up by a primarily for these four, is then going to be the question of, are all the eigenvalues at least negative or 0? That guarantees that nothing will explode to infinity. Asymptotically stable means that it will be, the norm goes to 0 as time goes to infinity. Great. That typically means that in LTI case that the lambdas all have to be less than 0. The funny thing is that the minute I start having time-dependent inputs, I can do some very crazy things that can cause some trouble here. So you have to deal with that in a more general case and have to deal with the more general solutions for these systems. There's also then the last case, which is exponentially stable, which means is the y of t sort of bounded by some negative lambda sort of decreasing time as I go towards t goes to infinity, where I have a positive c, so I can bound this. And so in LTI, again, this is basically going to be less than 0. For all eigenvalues, we get that. There's the last part of this, which you talk about, is bounded input, bounded output stability. And there's a couple different metrics you can use there as well, but basically the core of it is this, that you must have stability. It sort of extend, you have to extend to assume that if I have bounded inputs, the thing is still stable. So if I do something interesting with my inputs u of t, I got to make sure that no matter what I do with that, I'm not hitting any place that's all of a sudden going to kick the dynamics in an unstable way. Okay, so that's the part of it. But for many cases, we're often dealing with linear time invariant systems. At least that's typically going to be a lot of the examples. It's a little bit easier to kind of make sense of. Certainly if you're dealing with certain fixed mechanics systems, that's often what you see. If you're dealing with circuits, just what you see, and so on. And so one of the things you start worrying about is then what does the stability look like for your LTI system? The key is almost always going to be, when I look at these four cases, I'm looking at what is my A matrix. So if I imagine I have an A matrix looks like this, I would simply, 2 by 2, I compute the eigenvalues, and what I find here is that, yes, my eigenvalues are negative, right? But they are complex. Well, they're negative, at least in the front, but over here I get plus and minus. These are not complex. The lower one, I always get it negative and it's complex because it becomes the J term. But in the top case, not so much. And what happens is that one of the roots, square root of 3 over 2, is bigger than a half. And so adding that to 1/2 means, guess what? It's going to give me a positive root and I'm going to get instability. So this is the way you typically solve these problems. And it typically gives you a number of different options of how you put this together. But again, it allows you to kind of find your eigenvalues and then solve it accordingly.